But I'll be talking about Urbit. And Urbit is one way I'd like to talk about, since this is a functional programming group, is in one sense, it's what if our whole computational stack was functional programming? So our assembly language is functional, our systems language is functional, our operating system is something like FRP. It's a function that processes events and returns a new state rather than just maintaining memory and thread pointers as its state. So we'll talk a little bit about it. A lot of talks on Urbit, a lot of the design on Urbit starts at a very high level of like, okay, what is this thing from a user's perspective or a developer's perspective? I'm going to go up the tech stack because I think that's a really interesting angle for a group like this. So let me get my slides up here. So Urbit, when you read about it, gets pitched as a clean slate redesign of personal computing. So what do we mean by that? Well, in functional programming land, some of you might have actually seen this. This was an article from 1971, I think, from one of the ACM proceedings. And this was John Bacchus, who you might have heard of from BNF Grammars, the Bacchus-Nair form. And he wrote an article called, "Can Programming Be Liberated from the von Neumann Style?" The von Neumann style is this idea that we have an instruction pointer that points at some instruction for the CPU, and we have this array of memory, and the instruction works on the memory, and then you bump the instruction pointer, or for a few instructions, you might more than just increment, but you might actually mutate the instruction pointer depending on the state or the result of the instruction, right? So that's how assembly language works. And then C is a layer on top of that. And all of the programming languages at that point were essentially macros-ish on top of that. So this is really where the idea of declarative languages, and in particular functional languages, got started. We had the lambda calculus, but no one had really thought about using the lambda calculus or algebras of functions to run on real computers until Bacchus talked about that. So we started being able to write programs just as expressions rather than as statements that evaluated expressions. So in C, you have an expression as part of a statement, and in Haskell or something else, you just write expressions. You don't really do statements, except we still needed to handle input and output. We still need to handle the awkward squad, as Simon Peyton-Jones called it. So we essentially invented a way in languages like Haskell. The best we've been able to do is to invent a way to use expressions to mimic statements. And that's, if you know this paper, you know that this is the paper that proposed using monads for I/O in languages like Haskell. And that works really well. It's really powerful. But you're still operating on the external world as if it's this, you're still operating as if your program has an instruction pointer, essentially, that just moves down through your monad bindings instead of through your C program. And now your actions, your von Neumann actions, are higher order, but they're still von Neumann type actions that the computer takes. I had a professor in grad school who liked to joke that Haskell was the best imperative language because of the I/O monad and monad transformers. So this is still, today, every day when I work at Plow, I work with this. This is how I interact with the rest of the world using the I/O monad in Haskell. So that's where we are right now with functional programming, and that is about how liberated we are from the von Neumann paradigm, which is to say a lot, but not all the way. So what's Urbit? Urbit is a new software stack. And it starts out with something called Nock. Nock is a functional tree-based assembly language. So Nock has no idea about memory as this array that can be addressed numerically. Nock operates on nouns, which will be familiar to any Lisp programmer. You have atoms and you have cells. And cells can contain other cells, or cells can contain atoms, and a cell is just two things put together. It's cons. And that's it. And even Nock programs themselves are just atoms. Or sorry, just nouns, not atoms. Versus the instruction set for your CPU, it's an imperative and array-based assembly language. I say array-based because it's memory, the thing it operates on, you treat it as a giant array, right? Your pointer is an index into an array. On top of that, we layer Hoon, which is a functional tree-based systems programming language. So Nock is very simple. It has 11 instructions, I think, and it's something where you can actually understand programs written in it with some effort. It's not as obscure as trying to read the assembler that trying to regenerate from the assembler that Haskell spits out what the Haskell programmer is. But Hoon layers on a bunch of nice higher order features on top of that. And it would be equivalent to something like C or C++ on your standard ISA, where, again, these are imperative array-based systems programming languages. And then we get, and this is where things really start to get interesting, Urbit does not have an operating system. We explicitly say it has an operating function. That operating function is called Arvo, and it is several thousand lines of Hoon, but it is a function that takes in an event that needs to be dealt with and returns some output events and a new state. So every time you get an event, you take your current state and the event, you feed it to Arvo, and you get back some output events and a new state that you'll feed to Arvo next time. And this is the entire structure of Urbit at the systems level. So right now, all of this works. It runs. There's a VM that runs Nock. It's called Vir. It actually runs it somewhat efficiently, and you could actually do real things with it. Compare this to your Windows, your Linux, your Darwin, if you're a Mac guy, if you're doing embedded stuff, something like VxWorks, or even something like House, which was an attempt to write a whole operating system in Haskell. These are all interrupt-based operating systems. And what that means is anytime you do input, anytime you get input, you are interrupting the standard flow of the operating system and saying, hey, actually do this other thing. But while you're not doing that, your operating system is continuing with the von Neumann process of increment the instruction pointer, do the next thing, increment the instruction pointer, do the next thing. And even when you run an application on top of this, the application takes over control, and the way the operating system takes back control is to interrupt the application. So on top of that, we have a new identity and networking stack. So we have something called Azimuth, which I am saying is distributed and allodial identity. So again, we'll discuss what these things mean by comparison. You could compare it to your Unix username. That's allodial, and what that means is you control that username. You can, if you have your own Unix box, you can go in, make a user, delete a user, rename a user. You could change the password and tell someone else the password, so now they have the ability to run as that user. But it's local to that Unix box, right? So if you want to use that user from some other computer, you have to have some other way of identifying the Unix box that it's running on. There's also DNS, which is identity for computers, IP addresses, whatever, which is distributed. I can look up a DNS address anywhere in the world, but it's leased. I don't control it. I pay someone for the privilege of using it for a year, and I really only have human recourse if they cheat me on that, right? There's no technical resource for, hey, someone stole my DNS name. I have to go through people and have them decide in my favor to get that done. So I don't really control it in the same allodial sense. And then we have online accounts, everything from your Gmail to your Facebook, your Twitter, your Twitch username, anything where you have a username and password, your bank username and password. These are federated in the sense that each one is its own system, and they're tenuous, right? You have almost no control and no recourse if this is stolen from you, right? Someone else runs it. They more or less consider it their property that they allow you to use so that they can identify you. So with Azimuth, you actually own, and as of right now, it's actually implemented on the Ethereum blockchain, you own a numeric identity point that is translatable into a pronounceable username that you can set the private key. You can set a public key to be associated with that point, and only you can do that. And nobody else can take that away from you. No one else can come in and say, actually, we need to ban this person from using this identity on the system. Nobody else can come in and change your private key unless they get a hold of your Ethereum wallet. So what this means is I now have an identity that I control, but it's distributed. Anyone can go look up that identity, look up the private key associated with that identity, but nobody else can change what result someone would get if they went to look up that public key. Along with Azimuth, we've built something called AIMS, which is peer-to-peer, end-to-end encrypted, and identity routed networking. So when I use Urbit networking, I don't use an IP address, I don't use a system address. I simply use this Azimuth identifier for the Urbit, for the person that I want to communicate with. And the system figures out how to get it there. So even from a programmer's perspective, this is still what I'm handling. I don't ever write stuff to do with ports or IP addresses or anything. I write Azimuth identifiers as the addresses for my AIMS networking. Compare this to IP, where it's address routed, it's unencrypted at the base layer, it's technically peer-to-peer, but everything built on it, and all of the overlays that we've built, everything from network address translation to autonomous system space routing, is optimized for client-server-based communication. Right? You can do peer-to-peer over IP, and with Urbit, we use IP right now as our underlying transport, UDP and IP. We have to work around this part because most people running at home are using network address translation, and we have to work to give you peer-to-peer over IP. On top of that, we built a new application paradigm. And this is called Gall. And Gall is, again, instead of your application being another von Neumann system with one or more incrementing instruction pointers working on a shared array state, it's a collection of functions. They share a state in common, and each of these functions is responsible for some kind of event coming in and updating the state in response to that event. So given all this, what does it do? What's the point of building it this way? Well, one of the immediate benefits that falls out is it makes applications into programmable services, because every application has, first of all, a publish subscribe interface. When you build a Gall application, that is one of the things that you build, one of the interfaces you have to the world, is you provide a publish subscribe interface, and you can subscribe to other applications' publish subscribe interfaces. And again, this is just handled in a event-based way, where in response to any event, including a timer event, you can publish something on your interface, and one of the events you can respond to is an update to a subscription that you subscribe to. There's an RPC interface, which allows you to trigger an event for something that has not subscribed to you. So this is a way of initiating communication in a push-based fashion rather than in a pull-based fashion. And there's an immutable namespace interface, so you can build this immutable path-based namespace that other applications can just go ahead and read. The next thing is that we talked about this a little already, but Urbit unifies network addressing and identity. And you kind of have to see this in action to see how cool this is. I've been working on WebRTC integration for Urbit. And so you have some stuff that runs on Urbit, and then because it's WebRTC, there's some JavaScript that talks to Urbit, and there's a nice JavaScript wrapper for you to build WebRTC applications with. But literally, if you are trying to call someone, you just write their identity into, and that's all you have to do. There's no username password management. There's no third-party API integration for identity and authentication. There's none of that. You just write their identity in, and you could start initiating communication with them. A ship, which is a running instance of Urbit, has a point in the public key infrastructure that it provably owns. Anyone can go look up and say, what's its public key, and then use that public key to check if messages from it are valid and to encrypt messages to it. And the routing infrastructure of Urbit, the peer-to-peer routing infrastructure, will discover a route that you can use to send messages directly to that ship. And again, both at the application level and at the OS level, if you want to send a message to another Urbit instance, you just write in that point in the PKI. It's just a number, a pronounceable number that that you can write in. There's no complicated challenge response schemes. There's no keeping an index table of who goes where. This is all implemented for you once, and you just have to write in the identity that you want to talk to. Another really neat thing that Urbit does is it makes networking transparent. Remember, we talked about, we have pokes, which are sort of RPC calls. It's a push-based interaction with another application. We have watches, which are sort of publish, subscribe models, and scries, which are just sort of go get this data. And you could do this on another ship, and it looks exactly the same as doing it on your own ship. I can subscribe to something on a remote ship, and all I do is just change the parameter for where I'm subscribing to from my ship. There's a special variable that's my ship to whichever other ship. I can send a poke across the network to another ship, and it looks exactly the same as sending a poke to something on my local ship. All this is taken care of for you, so all you have to do is say, I want to watch this thing from over there. I have to poke it, or I want to poke it. I want to get this data from over there. And Urbit guarantees exactly once in-order message delivery from one ship to another. So Arvo and Ames will take care of making sure that your messages aren't going to show up out of order, that you're not going to receive duplicate messages. Each ship keeps a running counter of messages that it has sent to another ship and messages that it's received in order to guarantee this property. And there's exponential backoff retry in order to make sure that this happens. So right now, if you're just want to jump in and use Urbit, what's built on it right now? Is this just some interesting little experiment, or are people actually using it for things? So right now on Urbit, one of the things people are doing the most is chatting. There's peer-to-peer group chats, some very big ones, in some that number several hundreds of users. There's direct peer-to-peer DMs. These groups also support long-form writing, essentially blogs. There's a chess app. There's flashcard apps. There's a calendar. So this is what exists right now as sort of proof of concept of we're building real applications on this. But what's coming up soon is even more exciting. I think I mentioned I'm working on WebRTC stuff. It's already working for data channels. The video part is a this week or next week time estimate. That's when I expect the first video call over Urbit to happen. Right now, the Bitcoin payment infrastructure for Urbit, direct, and again, remember you have Urbit ID. There's no complicated authentication scheme. This allows someone to sign with the key associated with their Urbit and say, this is my address. If you want to pay me, please send to this address. And now we have payments integrated into Urbit. The Bitcoin part exists right now. It's just being audited and tested. The Lightning Network stuff is being built. And the file hosting infrastructure opens up something that gets talked about a lot, which is commoditization of infrastructure on Urbit. So instead of centralized hosting, instead of everybody uses Amazon for S3, or maybe they use Microsoft instead, if you have some storage, it's very easy to offer it, maybe for a fee, maybe not, to say these people can use it, and then offer it in a way that is integrated so that your other applications on Urbit can use it. So this is something that is in alpha right now, and the user experience is being built up and will be available very soon. There's a lot more that's being built. It's started to be a trend for infrastructure projects to have a awesome repo that's just a README linking to all the projects that are being built with it. So of course there's an awesome Urbit repo. You could see a bunch of the things that are being built there. And if you want to try out Urbit right now, it's very easy. The instructions at urbit.org/getting started will get you up and running and trying out the network. So with that, are there any questions? Scott, I can't hear you at all. Actually, you're muted.
Oh, sorry. So yeah, I have a couple questions. I don't know that I see any on the chat. So one question I have is, there's a lot of layers of this stack. Has much work been done in terms of being able to talk to things that are sort of outside of the Urbit stack? So if I have my Urbit personal computer and I'm trying to talk to some other device, what is that like?
So the principle, which doesn't hold as much anymore, but the original principle, because of one of the original blog posts that was made about Urbit, we tend to refer to Urbit as Mars and everything else as Earth. So the principle was expressed as Earth always calls Mars, Mars never calls Earth. But what that means in practice is, yes, even the way you use Urbit right now is you point your web browser at your local Urbit instance, and that's how you get the UI for chatting, for chess, for flashcards, for everything else. And that's already an instance of that, but that isn't just a browser HTTP thing. There's already libraries for Rust, for Haskell, for Go, for Ruby, Python, for a whole bunch of language to use on Urbit APIs. And remember, we mentioned we have a publish subscribe interface and a push-based RPC interface. And a namespace interface, all of these translate directly into HTTP API. So I can just use all of these things. I can poke something, I can watch something, I can scry something, which is that namespace lookup, over HTTP into my Urbit. So that's one direction. This is actually how the WebRTC integration works. There's stuff that runs on Urbit that handles that side channel that any WebRTC system needs. And there's and then there's the stuff that is written in JavaScript that actually sets up the WebRTC connection directly between the two browsers. This is also how the Bitcoin integration works. There's API integrations from Urbit to a Bitcoin node and vice versa. And the file hosting stuff works the same way. In Urbit, this is referred to as an airlock. The other side of that is that there's actually something built into the Urbit interpreter now that's accessible through Arvo to make HTTP requests from Urbit. So actually, if you go into Landscape, which is the main Urbit UI right now in your browser, there's a little weather app, and that uses that ability to go grab the weather from a third-party API service, just as an example of that kind of integration. So yes, Urbit can integrate in both directions. It can expose an HTTP API to other applications running on your computer, and it can make HTTP API requests.
Okay, yeah, no, that's a great answer. Are there other questions? So I guess another question that I have is, I saw that the WebAssembly is I'm sorry, not the web, the assembly language. Was that Nock? Is that the assembly language? Yeah. I saw you said that's running sort of like a functional approach. Has somebody tried to build that in hardware at all, or?
It's been actively discussed. It has not yet, to my knowledge, been built on an FPGA. Yeah. There's not really any. The thing is, there's not really any technical obstacle to doing that aside from somebody with the time and $1,000 FPGA actually doing it. But it's not yet been implemented directly in hardware. The other little bit about that is because Nock is so small in terms of its specification, it's missing a lot of the things that most specs include as a make it go fast thing, to the point where the only mathematical operation in Nock is increment, not add, but increment. And so you have to write add as Pinot style add and all the things that go with it. But this is fine because, again, Nock is a spec. And if you can write something in your interpreter that looks at a Nock function and says, hey, I can do this faster, then you can just go ahead and do that. And as long as it returns the same thing that the Nock function eventually would have, then that's fine. You've not broken it. And the Nock spec explicitly contemplates this. And so this is the idea of jets that sometimes gets mocked on Hacker News, but actually in practice works really well, and also means that if and when Nock does run on hardware, you can build faster hardware that does more optimizations, smarter optimizations, without changing your ISA, because your ISA is a spec, and you don't get to worry about the hardware implementation details. So you can have hardware jets, you could have a hardware implemented add that just recognizes the Nock add function and does an actual add in an ALU instead, and then gives you back what the result would be.
Is it your responsibility when you're working with that? So like, I mean, I'm a little bit familiar with that sort of like an external call to some other system to compute a result that your assembler would have computed. Mm-hmm. Traditionally that would be my responsibility as a programmer to make sure that my response is correct. Is it is that checked for me in any way, or is it once again my responsibility?
It's the shared responsibility of the standard library authors and the runtime implementers, whether that runtime's a VM or hardware, right? So we're building a standard library in Hoon. We see the Nock that Hoon spits out, and then we tie the jets to that Nock, and then everybody else uses that standard library. And again, in practice, this is working quite well. Nock isn't as there was actually a big discussion on Urbit yesterday where someone was saying Nock isn't as fast as they want, and hey, could we make it go faster this way? And one of the complaints was the cache performance of the current interpreter. And the answer more or less is, well, it actually doesn't work as badly as you're saying because we can use it and without really any lag. And secondly, the flaw is in the interpreter, not in Nock itself, and provably so because there's already a better interpreter in the works.
That sounds really interesting. What are the plans for the new interpreter?
So, this is the part where I'm not 100% sure because the current interpreter is a little bit obscure because one guy wrote it by himself over the course of a decade. So this is, I'm not into the Urbit systems, so I'll have to defer that answer because it goes beyond my Urbit knowledge.
That sounds interesting, though. Anybody else have any questions? Well, I think to me the things that always catch my attention about Urbit are, first of all, that it's all functional, which is really, really interesting. And then secondly, the unification of identity and network location. Like, that's just such a powerful thing that, every application that I see, it seems like they're trying to do that. I guess one question I have is, you mentioned in your talk, you mentioned that the ID, you could just switch to another ID to subscribe to it. Is it pretty easy to not, or to, I guess the only thing is a problem that you could maybe get lost in the, in sort of a stream where you have it go local and then remote and then local?
Well, so you don't switch midstream, but your the API for subscribing to something, the way in which you subscribe to something looks the same. Every call that you issue to subscribe to something takes which ship you're subscribing to, which application on that ship, and then a path that's defined by that application. Right. So an application can expose multiple different subscriptions, and the paths are sort of how you identify between those. But if I'm running an app and another ship is running an app, and I want my application to subscribe to their ship, this is actually how the WebRTC thing works. They actually cross-subscribe to each other, and that's how they can send messages back and forth. But it's literally just I subscribe to this same app, but I just I just use the variable that holds the ID of the remote, and it is just a variable. It's just a number. But the operating system is taking care of verifying, going to the PKI infrastructure, verifying that the public key associated with that number matches the public key of the messages coming back. So it's all secure. It's just a lot easier than, hey, I have to go look up this username and then go look up the public key associated with this username and do other authentication checks. And it just works. It's just somebody's identity. You just, as a programmer, all you have to say is, I want to talk to this identity.
Impressive.
And the operating system has encapsulated all of the questions about authentication and authorization for you. But it's also done in a way that you can just get an identity and hold on, and it's the same identity across applications. You don't have one for Facebook and another for Google and another for your bank and another for that one obscure government agency that you have to interact with once a year. So you have one identity for all these applications, and no one can take that away from you except by actually stealing a private key from you.
Mm-hmm. Interesting. Well, I guess if nobody else has any questions, maybe we'll stop there. I could ask questions for like another hour, but I could also just ask Edward. So if you have any, feel free to hit us up on the Slack channel if you guys have questions later, and I'll get them over if I can get answers. But Edward, thank you so much. I thought it was super interesting.
Yeah, thanks, guys.
All right, thank you. Bye.